1 of the seminar. The insightful deliberations and thought-provoking sessions provided a strong academic foundation and set the tone for today's program. We sincerely thank all the participants for their active involvement and continued interest. It is now my privilege to warmly welcome our Day 2 resource person, Shri N. Karunakar, Assistant Professor, Department of Mathematics, Baptla Engineering College. He has approximately 30 years of teaching experience and has published research papers in the topic graph theory and topological indices of chemical graphs. He is a dedicated academician known for his clarity of concepts and effective teaching approach. We are confident that today's session will further enrich our understanding and provide valuable insights into the applications of linear algebra. I extend a warm welcome to all the faculty members, research scholars, students, and participants who have joined us from various institutions across the country. Your continued presence adds great value to the academic event. With these words, I once again welcome you all and wish the second day of the seminar a great success. Thank you, sir.
Chipin, sir. So actually, your mic is disabled. Actually, okay, no problem. I will start, sir. Okay. Good evening, one and all. This is Karnakar. I am thankful to the principal, management, and organizing team for giving me an opportunity to deliver a talk on the matrix world on the occasion of National Mathematics Day. Now, I want to start this session. Now, here actually we want to start the some basic definitions related to the matrices first. Actually, to start the matrices, linear algebra, we want to take the vector spaces, then we have to go for dimensions and so on. But my focus is only on the matrices and its applications. Now, I want to take a, remember that now a system of mn numbers arranged in a rectangular formation along m rows and the n columns bounded by the braces is called an m by n matrix. Once again, if there are mn number of elements available and they are arranged in the m rows and n columns, so that any two rows and any two columns have the same number of numbers, then it is nothing but a matrix. And it is denoted by, as it has m rows and n columns, it is represented as m by n matrix. And each element of the matrix capital A is denoted by Aij. If it is A23 is available, it is the second row, third column element. Such an arrangement is definitely useful in writing programs, especially for C and MATLAB programs. Now, I want to take some different types of matrices that are available in our curriculum. The first one is related to a matrix is said to be a rectangular matrix if the number of rows and the number of columns are not equal. So if the number of rows is not equal to the number of columns, then the matrix is said to be a rectangular matrix. And if the number of rows and the columns are equal, then it is said to be a square matrix. Otherwise, it is said to be a square matrix. Now here we mentioned two examples. Capital A is a matrix which contains all the types of numbers like rational numbers, irrational numbers, surds, and so on, 0. Now it is the first row of the matrix, second row, and third row. And similarly, it is the first column, second column, third column, and the fourth column. So it is a matrix which contains 3 rows and the 4 columns. So the size of the matrix is nothing but 3 by 4. And so clearly that 3 is not equal to 4. So this is an example for a rectangular matrix. When I want to discuss about the matrix capital B, it has 3 rows and 3 columns. It has 3 rows and 3 columns. So the size of the matrix is 3 by 3. Sir, is it audible, sir? For confirmation. Vasant Kumar, sir. Sir, is it audible? Now, it is a 3 by 3 matrix. So as the number of rows and the number of columns are equal, then it is said to be a square matrix. So the second example is nothing but that is called a capital B, a square matrix, and a capital A is a rectangular matrix. Now, in the above 2 examples, the first matrix capital A is a 3 by 4 matrix, and the second matrix capital B is a 3 by 3 matrix. We can call it as a square matrix of order 3. There are some special matrices that are available. We can call it as a row matrix and a column matrix, because that column matrix is definitely so useful actually in the representation of eigenvectors of a matrix. So in case of a column matrix, it is of the form some 1, 2, 3, and 4. If a matrix has only one column, it is called a column matrix. If a matrix has only one row, it is called a row matrix. It is an example for a column matrix. I want to take some other example like a row matrix. It is some 1, -2, 3, and 4. Then I want to go for the determinant of a matrix. Let's wait. Then determinant of a matrix. Let us look at. Suppose if A is a 2 by 2 matrix, or if A is any matrix available for us, then determinant of a matrix is denoted by det A or nothing but modulus of A format. Actually, it is nothing but a function from a matrices to a real number field actually. If a capital A is a 2 by 2 matrix, if a capital A is a 2 by 2 matrix, let's wait. 2 by 2 matrix, or we may call it as it is a matrix of order 2, and assume that capital A contains elements of the form simply A, B, C, D, then the determinant of the matrix is defined as nothing but AD, BC. AD minus BC. So always it is nothing but, so input is nothing but a matrix, whereas output is a real number. So we can call it as it is a function, F is a function from a matrices to the set of all real numbers. We can define it is nothing but a function. Whenever there is a function is available, obviously we can define a linear transformation. Not all the functions are linear transformations, but if I take f of a alpha plus b beta is equal to a into f of alpha plus b into f of beta, then it is called a linear transformation. Whenever there is a matrix is available, always it is a linear transformation. Now let us continue the basics of the matrices. Now I want to take B is a 3 by 3 matrix. Only determinant can be applied only for square matrices. So if a B is a 3 by 3 matrix, the determinant of the matrix capital B is wait. The determinant of the matrix can be, the determinant of this matrix capital B is denoted by determinant of capital B, which is nothing but modulus format, not modulus actually. It is called a determinant format, A11, A12, and so on. If you expand the determinant along the first row, that is this is the expression for the determinant expansion of a 3 by 3 matrix. And whenever there is a term, it is A22, A23, A32, A33. We have to take some AD minus BC format for each and every determinant of this one. It is the second and it is the third. We can find, because these concepts are more important in finding rank of a matrix by using exact definition. I'm repeating that these definitions are more important in finding the rank of a matrix. Now I want to take minor of a matrix, minor of an element of a matrix. and minor of a matrix. So if A is any square matrix, if a capital A is any square matrix, then minor of an element is defined as the determinant of the matrix after removing the ith row and jth column, the corresponding element. So wait. It is the resultant matrix from capital A by removing the ith row and jth column from capital A. Now here actually I want to take the, let us go for, I want to take the element simply 6, assume that. Then what is the minor of the element 6? So we have to remove the proportionate row and the column. We'll get 4 elements. So let us take the determinant of 1. It is 3 and 3 and 7. So the value is equal to 7 minus 9, that is equal to minus 2. So this minus 2 is called the minor of the matrix. Sorry, minor of the element 6. But whereas here I mentioned, please wait. Here I want to mention the minor of the element 2, because the element 2 is available in the first row, second column. It is the first row, second column. Remove the proportionate row and the column. The resultant matrix is nothing but 5, 4, 3, and 7. So as I mentioned here, it is 5, 4, 3, 7. The value of the determinant is equal to 23. So because there are 9 elements are available, we can find minor of each of the elements, because those concepts are definitely useful in finding determinant of a matrix, and the determinant of a matrix is more important in finding the rank of a matrix. Now there are 3 elementary transformations that are available on the matrices. There are 3 properties that are available in the matrices. So interchange of any 2 rows or the columns. So if I want to take ith row, interchange with jth row, or I can interchange jth column with the ith column. Ci interchange with Cz. So I can interchange any 2 rows or I can interchange any 2 columns. It is called an allowed operation or allowed transformation. And the second elementary transformation is, you can call it as multiplication of any row by a non-zero constant, adding the elements to the corresponding row to the next row. It is Ri gives Ri plus k into Rj. Addition of a scalar multiple of one row to another row. And the third one is nothing but interchange of any 2 rows. Remember that these operations are allowed only on matrices, but not on the determinants. I'm repeating that. These properties are allowed only on the matrix, but not on the determinants. If you multiply any row by a non-zero constant in the determinant, the value of the determinant increased by k times. So these properties are allowed only in the matrices, but not on the determinants. Next, 2 matrices are of the same size are said to be equivalent, not equal. 2 matrices of the same size are said to be equivalent if one matrix is obtained from the other by a sequence of elementary transformations. So assume that capital A and capital B are 2 matrices of the same size. Assume that A is a matrix of size m by n and the capital B is also a matrix of size m by n. Assume that both matrices of the size m by n, then the 2 matrices are said to be equivalent. It is not equal, equivalent. If one matrix is obtained from the other by a sequence of these 3 operations. So by applying these 3 operations on capital A, if it is reduced to capital B, then the 2 matrices, capital A and capital B, are said to be equivalent, not equal. Now, I want to go for rank of a matrix, a more important property in finding solution for the system of equations. So, rank of a matrix, a very useful and what it calls more applicable point as far as the matrix or nothing but system of equations are considered. Rank of a matrix by definition, a matrix is said to be of rank small r. It has at least one non-zero minor of order r, and every minor of higher than r vanishes. So to say that 3 is a rank of a matrix, please wait. To say that 3 is a rank of the matrix, we can find a 3 by 3 submatrix for the given matrix whose determinant is not equal to 0. But the more important is all higher order matrices or square submatrices 4 by 4, 5 by 5, and so on. All square submatrices of the given matrix has the determinant is equal to 0. If both the conditions are valid, then the number 3 is said to be the rank of the matrix. But there are some special matrices that are available. All of you know that zero matrix is a matrix or nothing but a null matrix is a matrix. So let us look at it is nothing but an identity matrix of size 2. So rank of the matrix is equal to 2. It is a matrix of size 3 by 3. So rank is equal to 3. There is no rule that we have to find rank only for square matrices. We can find rank for rectangular matrix also. There is no rule that we are calculating rank only for square matrices. But the identity matrices, by definition, they are always square matrices. So I want to mention it as nothing but like this. So rank of an identity matrix of order n, I'm repeating that. Rank of an identity matrix of order n is n, because I want to mention rank of an identity matrix of order 2 is 2. Rank of an identity matrix of order 3 is 3. Rank of identity matrix of rank 3 is 3. Now, examples to find the rank of the matrix by using definition. So, first of all, I want to mention what is the exact definition to find the rank. Then we'll modify or nothing but we'll apply a technique that is called echelon form to find the rank of a matrix. So basically, as I mentioned, a number small r is said to be the rank. It has at least one r by r submatrix whose determinant is not equal to 0, and all higher order determinants should vanish. Now please look at, now I have a matrix capital A which contains some elements 1, 2, 3, 5, 4, 8, 12, 15, -2, -4, -6, and 10. So I have a matrix which contains, please wait. I have a matrix of size 3 rows and 4 columns. All of you know that. But remember that to get a 3 by 3 submatrix from the given matrix, I have to remove exactly one column. As there are 4 columns are available for it is the first column, second column, third column, and the fourth column. If I remove one of the 4 columns, I can definitely get. Suppose if I want to remove the first column, keeping the second column, third column, fourth column as it is, I can definitely get a 3 by 3 submatrix. I'll get a 3 by 3 submatrix. This is the 3 by 3 submatrix by removing the first column. Similarly, I can remove the second column. I'll get another 3 by 3 submatrix. I can remove the third column. I can remove the fourth column. I will get 4 3 by 3 submatrices for the same matrix. Suppose I want to call here, as I mentioned, A1, A1 is the submatrix of capital A by removing the first column. So I want to remove the first column. Let us take the resultant matrix is nothing but 2. I already copied only the element, that is these 9 elements: 2, 3, 5, 8. I want to just repeat: 2, 3, 5, 8, 12, 15, minus 4, minus 6, and 10. Now there are actually 9 elements are available. These elements are obtained by removing the first column of the matrix. Now, once again, I want to mention the matrix capital A. And as I mentioned, A1 is the matrix obtained from capital A by removing the first column. I'm repeating that from the first column. So it is the resultant matrix available. And I want to call this matrix as simply capital A1. And I want to find the determinant of A1, that is, as we mentioned, format. Suppose if I want to make this number is equal to 0, use the operation from the properties of determinants. R2 gives R2 minus 4R1. The object of this operation is nothing but to make the element 8 is equal to 0. Then I want to use the operation R3 plus 2R1. I want to use two operations. The object of these two operations are nothing but making the number 8 is equal to 0 and minus 4 is equal to 0. Now, please wait. Now, when you use the operation, it is 2. The number 2 will be copied, 3 will be copied, and 5 will be copied because there are no changes in the first row. If I use the operation R2 minus 4R1, remember that multiply your first row with the minus 4, add the elements to the next row. It is 0. It is a minus 12 plus 12, 0. Please wait. And it is a minus 15 minus 20. As you know that it is a 15 minus 20 minus 5. If I use the operation R2 plus 2 R1, it is, I want to make it as plus 2. 2 into 2, 4. 4 minus 4, 0. And it is 6 minus 6, 0. And minus 10 plus 10, 0. As your last row completely 0, the value of the determinant is equal to 0. So if I remove the first column, the determinant of the resultant matrix is equal to 0. Even when you apply the same set of operations on capital A2, the meaning of A2 is the matrix obtained from capital A by removing the second column. A3, the matrix obtained from the capital A by removing the third column. And A4, the matrix obtained from capital A by removing the fourth column. With the same set of operations, always your entire last row becomes simply 0. So determinant of A2, determinant of A3, determinant of A4, all are equal to 0. The meaning of that is you cannot find any 3 by 3 submatrix for the given matrix whose determinant is not equal to 0. So as I mentioned here, A has no 3 by 3 submatrix whose determinant is not equal to 0. Hence, rank of the matrix cannot be 3. So when it is not 3, then we have to go for lower than that number. That is, it may be 2 or it may be 1. So one more important point is, as the size of the matrix is equal to 3 by 4, always a rank of the matrix, remember that rank of the matrix is always less than or equal to minimum of m comma n. It is minimum of 3 comma 4. As minimum of 3 comma 4 is equal to 4, so the maximum possible rank is equal to 3. So rank may be 3. If it is not 3, maybe 2. If it is not, it may be 1, but cannot be 0. Remember that, because if it is a non-zero matrix, only 0 matrix has rank 0. If it has at least one non-zero element, the rank of the matrix is at least 1. Now we have the matrix capital A is available. Now I want to take, please wait, I want to take some other submatrix from this to get the rank of the matrix. Because that space is useful for us. Now I want to take a 2 by 2 submatrix for the given matrix. Remember that there are, because it has 3 rows, as I mentioned several times, and 4 columns. I want to get all 3 by 3 submatrices is equal to, has a determinant is equal to 0. Rank cannot be 3, as we mentioned here. Now I want to discuss about rank 2. So suppose if I want to take a 2 by 2 submatrix like this, assume that the determinant of the matrix is 8 minus 8 is equal to 0. So it has a 2 by 2 submatrix whose determinant is equal to 0. Suppose if I take this, if I take this 2 by 2 matrix, it is 24 minus 24 0. But if I take please wait. But if I take something like this, assume that is the 2 by 2 submatrix, it is 45, determinant of that matrix 45 minus 12 into 5 16, which is equal to minus 15 is not equal to 0. The meaning of that is the matrix has a 2 by 2 submatrix whose determinant is not equal to 0. So obviously rank of the matrix is equal to 2. The more important is because how many 2 by 2 submatrices can be formed with this matrix? I'm repeating that. How many 2 by 2 submatrices can be formed from this matrix? So when you observe this, to get a 2 by 2 submatrix, to get a 2 by 2 submatrix, we have to remove one row and two columns. One column can be selected exactly C3. Sorry, it is, I think it may be 2 by 2, correct? It is 4C2. Okay. Two columns are required for us. So it is a 4C2. Two columns are required. So two columns are not required. So the number of ways of selecting two columns from the available four columns in 4C2 ways. There are three rows are available and I have to remove one row that can be selected in C31 ways. 4C2 is equal to 6 and 3C1 is equal to 3. The total is nothing but 18 2 by 2 submatrices can be formed from this matrix. I'm repeating that 18 2 by 2 sub. So we have to check determinant of all these 2 by 2 submatrices. If we can find at least one 2 by 2 submatrix whose determinant is not equal to 0, we can say that the rank of the matrix is equal to 2. Otherwise, we have to go for some other definition. Now, it is nothing but one important point where we want to apply this technique to find the rank of a matrix. So, a matrix capital A is said to be in the echelon form. A matrix capital A is said to be in the echelon form. Every row of capital A has all its zero elements below a row which has a non-zero element. So, okay, we'll look at the things later. So the definition is whenever all the elements of a row are available, suppose the matrix is nothing but like this, always if there is a row is available, always it should be at the bottom of the matrix. Now, the second is the number of zeros before the first non-zero element in a row must be less than the number of such zeros in the next row. When a matrix which satisfies these two conditions is called echelon form of a matrix. Now, suppose if you reduce the matrix into the echelon form, the number of non-zero rows will tell you the rank of the matrix. One important theorem is available, which is called rank nullity theorem. But whereas we have to attempt what we call it as a dimension and basis of a vector space, then we have to attempt the nullity of the linear transformation. So we'll look at the things later, but just as it is a part of that, just I want to tell to you. Now I want to go for the next one. Finding this, wait, it is the yellow color. Finding the rank using the echelon form. As I mentioned, I want to take a matrix, find the rank of, because as I mentioned, this rank definition is more useful for us in finding solution for the system of equations. in finding solution for the system of equations. Now, find the rank of the matrix. This matrix, it is a matrix of size of 3 by 4. Actually, there is no rule that always we have to take 3 by 4, but I considered a 3 by 4 matrix always because as it is a rectangular matrix. So I want to take a rectangular matrix first of all. Now, to reduce the matrix into the echelon form, remember that. So use the elementary transformations. I want to find the rank of the matrix. So finding the rank using echelon form. Now, as I mentioned to you, look at this one. It is the first non-zero element of the row. I'm repeating that it is the first non-zero element of the row. And this is called the pivot. We have to make the elements below to that are equal to zeros. Below to that are equal to zeros. So I want to make the number 4 is equal to 0. And I want to make the number -2 is equal to 0. I'm repeating that as it is the first non-zero element of the row. I want to make the elements below to that are equal to 0. So the number 1 is called the pivot element of that row. Now, please wait. To make the number, this is 4 is equal to 0. I want to multiply. Remember that I want to use the operation R2 minus 4R1. Before R1, we have a number 4. Before 4, we have a sign minus. So multiply first row with minus 4. Just I want to write here into minus 4. The meaning of that is multiply first row with minus 4. Add the elements to the next row. It is a minus 4 into 1 minus 4. Minus 4 plus 4 is equal to 0. And minus 4 into 2 is equal to minus 8 plus 8 is equal to 0. And similarly, minus 12 plus 12 is equal to 0. 15 minus 20 minus 5. So by using the operation R2 gives R2 minus 4R1, my object is getting only 4 is equal to 0. But I got first 3 elements. First element is 0, second element is 0, and the third element is equal to 0. Then I want to make the number -2 is equal to 0 using the number 1. So I want to use the operation R3 plus 2R1. I want to use the operation R3. It's wait, I want to use the operation. It is, I want to make it as 2. 2 into 1, that is equal to 2. 2 plus -2 is equal to 0. Similarly, 2 into 2, 4, minus 4. So similarly, we can apply the same technique. Your entire last row becomes 0. As I mentioned in the echelon form, just I want to recall the previous slide. So echelon form of a matrix. So every row of capital A which has all its elements 0 before every row which has a non-zero element. The number of zeros before the first non-zero element of a row must be less than the number of such zeros in the next row. Now, remember that. Now it is a row which all elements are zeros. Here, the number of zeros before the first non-zero element is equal to 0. As it is the first non-zero element, before that, there are 3 zeros are available. As it is in the increasing order, the number of zeros before the first non-zero element. So this matrix, please wait. This matrix is in the echelon form. As it is in the echelon form, look at the number of non-zero rows. It is a non-zero row and it is also a non-zero row, whereas it is called a zero row. As it has 2 non-zero rows are available for you. So we can call rank of the matrix is equal to 2. So we completed the same problem with the 2 methods. The one is by basic definition, then by using echelon form. Definitely, this echelon form is more convenient to find the rank instead of applying the exact definition of a rank of a matrix. Now, special matrices and their ranks, let us look at. So, rank of an identity matrix of size n is n. As I mentioned to you, assume that it is 1, 0, 0, 1. It is called a matrix of size 2 by 2. 2 by 2 identity matrix, the rank is equal to 2. And identity matrix of order 3, 0, 1, 0, 1, 0, 0, and 0, 0, 1. The rank of the matrix is equal to 3. Similarly, we can find or we can tell the rank of any n by n identity matrix. N by n identity matrix is equal to n. So every non-zero matrix has at least rank 1. So if A is a non-zero matrix, then rank of A, it is denoted by row of A, is at least 1, so greater than or equal to 1. Rank of A is equal to 0 only if A is a null matrix or nothing but a zero matrix. As we mentioned, only the zero matrix is of rank 0. If A is a If capital A is a non-singular matrix, of course, when I call it as non-singular matrix, it is a square matrix of order n. Then obviously rank of the matrix is also equal to n, because if these are some special matrices that are available, but there is no rule if A is a matrix of size m by n. So zero matrix is always a rank 0. If it is an identity matrix of order n, that is always equal to n. If A is any matrix which is a non-zero matrix, rank is at least 1. And if capital A is a non-singular matrix, there is no rule that it is a identity matrix. Of course, those two are equivalent matrices, but not equal matrices. I want to use that rank to get the solution for the system of equations, a more important point related to the system of equations. And this arrangement is definitely useful in programming, especially for arrays. It is called first row, first column, first row, second column, and so on. Now, if you are very aware, know about the importance of the arrays, definitely you know that. Consider a system of, please wait. Consider a system of m equations with n unknowns. So it is the first equation. The unknowns are x1, x2, x3, and xn. This is the, once again, second also equation also contains the same set of unknowns. Remember that, same set of unknowns. So we have a system of, it is the first equation, it is the second equation, and it is the mth equation. Now we have a system of m equations are available. Look at unknowns. First unknown, second unknown, third unknown, and it is the nth unknown. It has a set of n unknowns are available. The object of this topic is we want to find the solution for the system of equations. But generally at your intermediate level, you may know that there are two techniques may be completed. One is the matrix inverse method and the Cramer's rule to find the values of x and y. What is the difference between that level and this one? Those two methods are useful for us if the system has a unique solution. And moreover, if the system has 4 unknowns or 5 unknowns, it is very difficult for us to test whether the system is consistent or not. What is the meaning of consistency? Suppose if the system is said to be consistent, it has a solution. The above system is said to be consistent if it has a solution. What is the meaning of that? To find the values of x1, x2, x3, and so on, xn, which satisfies all the equations, then those x1, x2, and so on, xn are said to be solutions of the system of equations. Once the solution is available, then the system is said to be consistent. Sometimes equations are available, but we cannot find a solution. Such a solution does not exist. Then obviously it is said to be inconsistent. So system has two possibilities. Please wait. System has two possibilities. The system may have a solution or system may have no solution. If it has a solution, it is said to be consistent. If it has no solution, then it is said to be inconsistent. Now let us discuss now the method to apply the consistency for the system of equations. So the matrix representation of the given system is nothing but like this. The matrix representation of the given system is nothing but A into X is equal to capital B. Now, capital A is the coefficient matrix, x1 coefficient, x2, I'm repeating that, x1 coefficient, x2 coefficient, x3 coefficient, xn coefficient in the first row, and x1 coefficient, x2 coefficient, x3 coefficient, xn coefficient of the second row, and similarly in the mth row. Capital B is the column matrix. Of course, I mentioned, just forgot it. So capital B is the column matrix which contains the elements B1, B2, and so on. As we have m equations are available, it is BM. Right? Capital A together with the capital B, it is called the augmented matrix capital A. Oh, it is actually not B, it is a capital K. It is not capital K, B, it is capital K. Let us look at capital K is equal to capital A together with the capital B, and it is called the augmented matrix of the system. It is called the augmented matrix of the system. Now, there is an important theorem that is called Rouché's theorem. There's an important theorem, Rouché's theorem, which is useful for us in testing the system of equations, because without knowing the basics, it is not easy for us to solve the system. So how many equations are available? There is no problem for us. We can apply the same technique to get the solution for the system of equations by using Rouché's theorem. The system of equations is said to be consistent if and only if the rank of the coefficient matrix and the rank of the augmented matrix are the same. As I mentioned, row of A always denotes rank of a matrix. It is a notation. And row of K is the rank of the augmented matrix capital K. So if rank of A and rank of K are equal, then only the system may have a solution. If the two ranks are different, then obviously the system has no solution. If rank of A is not equal to rank of K, then the system is said to be inconsistent. Once again, in particular, if a rank of A is equal to rank of K is equal to N, that is the number of unknowns, always N denotes the number of unknowns, the system is consistent and it has no solution. If the solution is available, there are two other options that are available for us. The first one is the system may have a unique solution, or the system has an infinite number of solutions. So if a rank of A is equal to rank of K is equal to smaller, less than the number of unknowns, then the system has infinite number of solutions. In particular, the solution set has n minus r unknowns. Let us go for a problem on this. I want to take solving the system of equations by using Rouché's theorem. I want to take finding the solution for the system of equations 3x plus 2y minus z is equal to 3, 2x plus y plus z is equal to 0, 6x plus 2y plus 4z is equal to 0. Remember that here we are required to find the solution for the system of equations. So the matrix form of the given system is nothing but like this. As I mentioned, the coefficient of x is equal to 3 in the first equation, quotient of y is equal to 2, quotient of z is equal to -1, and similarly the coefficients of x, y, z in the second equations. In the second equation, third equation. So it is of the form capital A into capital X is equal to capital B. As you know that A is always called the coefficient matrix, capital B is called the column matrix, and capital K is called the augmented matrix. Now we want to use Rouché's theorem to decide what is the solution or the solution set for the given system of equations. Now just I want to recall just the equations, whether you may forget as it is the next slide. So once we have the matrix representation is available for us, consider the augmented matrix capital K, capital A together with the capital B. Like in the previous, just reduce, as I mentioned, it is the first non-zero element of the row. Apply echelon form method to make these two elements are equal to 0. I want to make the number 2 is equal to 0 using the operation, because I want to make the number 2 is equal to 0. R2 gives, it is 3R2 minus 2R1. My object is I want to make the number 2 is equal to 0 by using the number 3. Just I want to mention that it is a 3, 2, 1, then 3. It is multiply the second row with 3, multiply first row with the -2. When you remember, there is no need to remember. Looking this one, you can say that is 6 minus 6 is equal to 0. it is a minus 2 into 2, minus 4. Minus 4 plus 3, it is a minus 1. And it is a minus 2 plus 3, it is 1. It is a minus 6. To make the number 6 is equal to 0, I want to use the operation R3 gives R3 minus 2R1. There is a multiply R3 minus 2. It is a minus, I think it is visible to you. Minus 2 into 3 minus 6 plus 6, which is equal to 0. Minus 4 plus 2. Minus 4 plus 2, it is a minus 2. Then minus 2 plus 4, it is a plus 2. Then I want to take a minus 6 and a plus 6, that is equal to 0. As you know that my object is getting this place is equal to 0 and this place is equal to 0. As I mentioned, to reduce the matrix into the echelon form, then only in a comfortable manner we decide the rank of the matrix. So it is the first row of the matrix, and it is the second row of the matrix. It is the third row of the matrix. As it is the first non-zero element, before to that, 1 0 is available. Here also 1 0 is available. So the resultant matrix is not in the echelon form. In the second row, 1 0 is available. So in the next row, we have at least 2 zeros should be there. So we have to make the number minus 2 is equal to 0 by using the operation R3 minus 2R2. Use the operation R3 minus 2R2. Before R2, I want to write multiply second row with minus 2. Copy first row and second row elements 3, 2, 1 and 3 as the first row, and the second row 0, minus 1, 1 and minus 6. As I mentioned, multiply second row with the minus 2. Minus 2 into 0, 0 plus 0, 0. Minus 2 into minus 1, 2. 2 plus minus 2, 0. Minus 2 into 1, minus 2 plus 2, 0. And minus 2 into minus 6, 12 plus 0 is equal to 12. So remember that there is a rule. When you move from top to bottom, the number of zeros before the first non-zero element should be increased. Here there are no zeros are available. There are zero number of zeros before the first non-zero element. Here there are exactly 1 0 is available. Here before the first non-zero element, there are 3 zeros are available. So the matrix is definitely in the echelon form. But when you observe that it is the matrix capital A, in the matrix capital A, we have only 2 non-zero rows. So rank of A is equal to 2 because it is a 0 row. Then I want to use some other color. Remember that it is 0 row in capital A. So rank of A is equal to 2. If I take a rank of K, so if I want to add the last column also 0, 0, 0, whereas it is a 12, rank of K is equal to 3. As the two numbers are not equal, the system has no solution. In other words, always it is the X coefficient, it is the Y coefficient, it is the Z coefficient. We cannot find X, Y, Z so that 0 into X plus 0 into Y plus 0 into Z is equal to 12. So obviously we can say that the system has no solution. So any doubts? Shall I continue? Shall I continue, sir? Any questions? As you know that, as I mentioned here, K is of the form like this. In K, it is simply capital A, rank of A is equal to 2. By including the last column, we'll get a rank of K is equal to 3. both are different, wherever two ranks are not equal, as we mentioned here, the system of equations has no solution, or the system is said to be inconsistent. We already completely solved in the previous slide to say that the system of equations are inconsistent or the system has no solution. Now let us go for, remember that it is a simply, suppose if the system of equations are nothing but like this. So there is no common point for all the three surfaces. There is no common point for all the three surfaces. So the system is said to be like this, maybe like this. They are not intersecting. Two planes are not intersecting, but whereas all the three planes are not intersecting at one point, so the system has no solution. Now I want to take some other example. Sir, is it audible, sir? Sir, is it audible?
Yes, it is audible, sir. You can continue, sir.
Okay, sir. Now I want to take solving the system of equations using Cauchy's theorem in the same model. We want to take, in the previous example, we completed a problem where the system has no solution. Always the system has three possibilities that are available. The system may have no solution, unique solution, and infinite number of solutions. And there are two more options that are available. There is no rule that in the previous example, we considered a system that contains three equations and three unknowns. Just I want to look at this one. We have three equations and three unknowns. It is the first equation, second equation, and third equation. We have a set of three unknowns, x, y, z. So this is the system which has three equations with the three unknowns, but there is no rule that we have to take always the number of unknowns and the number of equations are the same. Now here I want to take such an example. Look at, solve the system of equations, nothing but like this. It is the first equation in terms of x, y, z. It is the second equation in terms of x, y, z. Third equation in terms of x, y, z. Please wait. And it is the fourth equation in terms of x, y, z. So we have a system of four equations with the three unknowns. So I want to go for the matrix representation of the given system is nothing but like this. All of you know that x coefficient, y coefficient, z coefficient. It is 1, 2, 1, and 2, 3, 2, and so on. We can replace here. It is simply capital A, the coefficient matrix. The column matrix is a capital X, and this matrix is a capital B. So we want to take whether the system has solutions or not. So here we consider a system of four. Actually, when you discuss about this system of equations, this is nothing but first plane, second plane, third plane, and fourth plane. Whether all the four planes are intersecting at one point or not. If they are intersecting, what is the common point? That is the object of this method. Suppose if you go for more than 3 or 4, we have called it as hyperplanes. Now, this Cauchy's method is useful for us. Even there are n equations with the m unknowns are available for us. Now, let us go for it. Is the system always we mentioned here for our reference, and it is the augmented matrix of the system. Now, as I mentioned, like in the previous, as it is the first non-zero element of the row, we want to make these three elements are equal to 0. Using the element 1 or nothing but using the pivot element 1. Use the operations R2 minus 2 R1, R3 minus 3 R1, and R4 minus 3 R1. To make the number, this is 2 is equal to 0, multiply first row with minus 2. So all the first row elements are copied. There is no difference. Minus 2, as I mentioned, minus 2 into 1, minus 2 plus 2, 0. Minus 2 into 2, minus 4 plus 3, minus 1. Similarly, minus 2 into 1, minus 2 plus 2, 0. And it is a 5 minus 6 is equal to minus 1. Similarly, I use the element 1 to make this 3 is equal to 0 and this 3 is equal to 0. Using the operations R3 minus 3 R1 and R4 minus 3 R1. Always use the element 1 to make these three elements are equal to zeros. Now I want to, after applying those operations, it is the resultant matrix capital K. As it is the first non-zero element of the second row, the number is equal to -1. Then in the approaches that we have to reduce in the echelon form, make these two numbers are equal to 0. -11 should be 0 and 3 should be 0 by using the number -1. So I want to use the operations R3 minus 11 R2. And to make the number 3 0, it is R4 plus 3 R2. If you operate those two, there is no change in the first row. 1, 2, 1, 3. There is no change in the first row. And similarly, there is no change in the second row. 0, -1, 0, -1. When you go for the third row, as I mentioned, R3 minus 11 R2, multiply your second row with -11. If you write -11 here, it is definitely more convenient for you in calculating the third row elements. -11 into 0, 0, 0 plus 0, 0, -11 into -1, 11, 11 plus -11, 0, -11 into 0, 0 plus 2 is equal to 2, and it is a -7 plus 11, that is equal to 4. Then to make the number, of course, this element becomes 0. It is so clear. I want to make the number 3 0. R3 plus 3 R2. Please wait. I want to remove this. So I want to multiply second row with the 3, multiply with the 3, and add the elements to the fourth row. It is a 3 into 0, 0, 0 plus 0, that is equal to 0. It is -3 into -1, -3, -3 plus 3, 0. It is 3 into 0, 0, 0 plus -4, -4. It is a -3, -5, it becomes -8. Now, when you look at this one, we have, it is the first non-zero element of the second row. The number of zeros are equal to 1 before the first non-zero. It is the first non-zero element of the third row. There are 2 zeros are available. Even in the fourth row, there are 2 zeros are available. So this matrix is not in the echelon form. As it is only 2 zeros are available in 2 successive rows, it is not in the echelon form. So I have to make the number -4 is equal to 0 by using the operation R4 gives R4 plus 2 R3. So if you operate this 1, 2, 1 with the 3 and 0, -1, 0, -1, 0, 0, 2, 4. Then when you operate 0, 0, 0 and 0, it is a third row multiply with the 2, multiply third row with the 2, add the elements to the second row. 2 into 0, 0, 2 into 0, 0, 0 plus 0, 0. It is 2 into 0, 0, 0 plus 0, 0. It is 2 into 2, 4, 4 minus 4 is equal to 0. It is 2 into 4, 8 plus -8 is equal to 0. Now, actually, the number of zeros before the first non-zero element, it has 1 0, 2 zeros, of course, 0 row. So it is in the echelon. When you move from top to bottom, the number of zeros before the first non-zero element should be increased. And if a row has all the elements are equal to 0, it should be below a row which has a non-zero element. Now observe this. Please wait. Observe this. It is a please wait. It is a non-zero row. It is a non-zero row. And it is a non-zero row because it has a non-zero. So rank of A is equal to 3. The rank of K is also equal to 3. But when you observe this, there are 3 unknowns are X, Y, and Z. So rank of A is equal to rank of K is equal to 3 is equal to the number of unknowns. By Rouché's theorem, the system has a unique solution. Of course, we mentioned all the elementary transformations here is weight. So this is the system of equations. By applying those operations, these are the matrices by applying these elementary transformations as your last row completely zero. And the number of zeros before the first non-zero element is 1. Now we have 2 zeros, which shows that the given matrix is in the echelon form. So the system has 3 non-zero rows. Please wait. Has 3 non-zero rows. And the rank of A is equal to rank of K is equal to 3, the number of unknowns. By using the Roux's theorem, the system has a unique solution. So then our object is how to get the solution for the system of equations. So the given system of equations can be rewritten as nothing but like this. X plus 2y plus z is equal to 3. That is already available here. Is the same first equation. Whereas second equation is nothing but minus y is equal to 1 minus 1. And from the third equation, 2z is equal to 4. So from this, the value of z is equal to 2. Sorry, is right. And from this equation, the value of y is equal to 1. Substituting these two values in the first equation, get x is equal to minus 1. You can call this by back substitution. So we'll get the values of x is equal to minus 1. We have y is equal to 1. And z is equal to 2. Once the values are available, we have very big doubt whether it is correct or not. If we substitute all the values in all the equations will be satisfied. For your convenience, just I want to take the last equation, whether it's correct or not. It is a 3 into, as you know that x is equal to minus 1, plus 9 into y is equal to 1, minus z. If we calculate the value, it is a 9 minus 3, that is equal to, it is a 9 minus, that is a 9. It's a 3 into minus 1 minus 3 plus 6. 6 minus z is equal to 2.
Unique solution, infinite solution.
6 minus 2, that is equal to 4. Similarly, all the equations will be satisfied. So the system is said to be consistent and it has a unique solution. We completed the two models. The system has no solution and the system has unique solution. Let us attempt one question related to infinite number of solutions. So it is an example diagrammatic representation of this one. Please look at this one. So the point is common for the first plane. Please wait, I want to take over. One minute. This point is common. For the first surface, look at this, it is the first surface. For the second surface, and the third surface, that is called horizontal surface. To know all the things, actually we have to know thorough with at least coordinate geometry. So 3 planes, they are intersecting at one point. If there is no common point is available, of course we can say that there are 2 possibilities that may be available. All the systems are intersecting. Remember, it is actually the diagram represents only 3 planes, but our problem contains 4 planes. There is some other plane is also available, nothing but like this. So all the 4 planes are intersecting at one point. The point is simply capital P. That point is called the solution of the given system of equations. Now let us go for some other problem. Investigate, test for consistency for the system of equations and find the solution for the system of equations. We have a system of 3 equations with the 3 unknowns. The equations are some 4x minus 2y plus 6z is equal to 8. It is a 4 minus 2, 6 and 8. Second row contains x plus y minus 3z is equal to minus 1. X plus y minus 3z is equal to minus 1. And the third equation is 15x minus 3y plus 9z is equal to 21. So once it is of the form Ax is equal to capital B, we want to say that whether the solution consistent or not. To say the solution is consistent or not. Let us consider the augmented matrix of the system. Capital K is equal to capital A together with the capital B. So let us take a capital K, completely capital A, together with the capital B. So as it is the first non-zero element, we can make these two terms are equal to 0 as the first option. We can do that. Or we can interchange the two rows. That is our choice. These type of operations are only in the matrices, especially in the system of equations, not in determinants. In determinants, if you apply that, you have to put minus sign before to the determinant. Now, I want to use interchange of two rows. The first operation that I want to use, interchange of first row. So all the first row elements should be copied to second row, and the second row elements are copied to the first row. As it is the first non-zero element of the row, I want to make these two numbers are equal to zeros by using the operations R2 minus 4R1 and R3 minus 15R1. So to make the number 4 is equal to 0, multiply first row with the minus 4. So multiply first row with the minus 4, add the elements to the corresponding elements of the second row. It is a minus 4 into 1, minus 4 plus 4, 0. It is a minus 2, minus 4, minus 6. And a 6 plus 12, that is 18. And it is 8 plus 4, that is equal to 12. Similarly, to make the number 15 is equal to 0, use the operation R3 minus 15R1. Obviously, it is 0. It is a minus 3. And it, of course, by the time we have to multiply first row with the minus 15. Then I will remove this, please wait. And there is no this number. It is minus 15 into 1, minus 15 plus 15, 0, minus 15 minus 3 minus 18. It is 9 plus 45, that is a 54, and it's 21 plus 15, that is equal to 36. As it is 0, it is the first non-zero element of the second row. We have to make the elements below to that are equal to 0. Implies that minus 18 should be 0. So use the operation R3 gives R3 minus 3 R2. So multiply your second row with minus 3. I won't write into minus 3 for our convenience. And use the operation. It is 1, 1, minus 3, and minus 1. No change in the second row. 0, minus 6, 18, 12, 18, this one. It is 12. Whereas when you multiply second row with the minus 3 into 0, 0 plus 0, 0, it is 18 minus 18, 0, 54 minus 54, 0, 36 minus 36 is equal to 0. If you operate R3 gives R3 minus 3R2, actually my target is only this element is equal to 0. But luckily or unluckily, I will get all the elements are equal to zeros.
For that one I can do, sir.
So use the operation R3 minus, please.
Okay.
Use the operation R3 minus 3R2, you'll get all your third row becomes 0.
No, but it is not opening, sir.
So we have only two non-zero rows. Please wait.
It is also strange, sir.
So it is a
my
non-zero
other
row,
account also it is
and
not
it is a
opening.
non-zero row.
Observed it.
So rank of A,
Yesterday also I saw that.
rank of A is obtained by just removing the last column. It is a non-zero row. I think it is visible to you. It is a non-zero row of A. It is a non-zero row of capital A. So rank of A is equal to 2. Similarly, when you take rank of K is also equal to 2.
I don't know who is that.
But as you observe that there are three unknowns are available in the system.
The question, but we are not able. Actually, from our branch itself, 4 members are available.
It is the first unknown, second unknown, third unknown. If you compare rank of A is equal to rank of K is equal to 2, rank of A is equal to rank of K is equal to 2. Compare with the number of unknowns, then the system is consistent and it has infinite number of solutions.
Okay, sir.
But actually, when right hand side is equal to 0, then it is said to be, you can apply rank nullity theorem because that is somewhat different. There is a transformation available. It is a vector space capital V to a vector space capital V, and a T is a linear transformation from capital V to capital V. It is called dimension of the vector space capital V. So rank T plus dimension of T is equal to, sorry, rank T plus nullity T is equal to dimension of the vector space. It is called rank nullity theorem. Now I want to go for, I'm not touching the vector spaces and so on because that is somewhat different topic, which is useful especially for CSC students syllabus. Moreover, the solution set contains 3 minus 2 is equal to one independent solution or one parameter. So the given system of equations can be rewritten as, I remove this one. We have 3 minus 2 that is equal to one parameter. Now the equation from the first equation we can mention it is x plus y minus 3z is equal to 1. From the second equation minus divide every row with 1 by 6 because we have an allowed operation multiplication of any row by a non-zero constant. Multiply your second row with 1 by 6 minus 1 plus 3z is equal to 2. So from the second equation, y is equal to 3z minus 2. I think as I mentioned, y is equal to 3z minus 2. And substituting y is equal to 3z minus 2 here, we get x is equal to 1. So the solution set is, your first component is nothing but x. If I take z is equal to k, assume that if I take z is equal to k, from your y expression, y is equal to 3k minus 2 and z is equal to k. This is not called a solution, it is called the solution set. Because if the value of k changes, we get a different solution. As k has infinitely many number of values, possible values. So it is called a solution set, but not a solution. Now remember, it is like a book. Remember that. So here we can take, there are three equations are available. This plane, sorry, this line is common. This line is common for the first plane, for the second plane, and backside third plane. So this plane is, so this line is common for all the three planes. As it is a line, as I mentioned to you, the number of points on the line is equal to infinitely many. So you can call it as it is it is simply like that. So sometimes you may get 4 planes with the same common line. So that is called, the system may be consistent and the system has infinitely many number of solutions. We have the homogeneous system of equations. It is almost like the previous model, but the difference is on the right hand side, there is some zero mistake actually. Always the right hand side, every term is equal to 0. So in the previous, we have B1, B2, B3. Now we have all the constants are equal to 0. Such a system is said to be a homogeneous system. Please wait. This is called a homogeneous system. Now, remember that always in this type of systems, always we have a solution. Always, such a solution is called a trivial solution. X1 is equal to 0, x2 is equal to 0, x3 is equal to 0, and so on. Xn is equal to 0 is always a solution available for us. Without solving the equations, we can say that it is a solution. But our concentration is, can we find a non-zero solution or not? Remember that these concepts are more useful, especially in vector spaces. In the vector spaces, a set of vectors are linearly independent or not. These conditions are more useful for us. After a homogeneous system, generally, what we will do is explaining the vector spaces, then dimension of the vector space, then basis, independent and dependent set of vectors, then we have to go for rank of the matrix. Now, I'm not touching those, as I mentioned several times, I'm not touching those concepts, but at least you must know that it has very good applications. So our concentration is, this is a system of m equations are available with n unknowns. On the right hand side, we have every term is equal to 0. 0, 0, and 0. It is called a homogeneous system. It has first equation, second equation, mth equation. And as I mentioned, first unknown, second unknown, third unknown, and it is the nth unknown. So a system of m equations with n unknowns, and the system is nothing but a homogeneous system. Here, there is no uh, possibility of getting no solution. We have only two possible cases that are available, like in the previous unique solution and infinite number of solutions in the previous case. Now we have zero solution and a non-zero solution. As I mentioned, always one solution is always ready for you. Without solving the equations, we can say that one solution is always ready. Such a solution is called a trivial solution or nothing but a zero solution. So trivial solution or zero solution is a solution. The meaning of that is every component is equal to zero. Suppose if a rank of A, please wait, there is no need to go for any augmented matrix here, just a rank of the matrix is sufficient for you. So if a rank of A is equal to n, then the system has only one solution, that is called the trivial solution. If capital A, the coefficient matrix of the above system is nothing but like this. If a rank of the coefficient matrix is equal to n, the system has only one solution, that is the trivial solution or zero solution. If a rank of A is less than n, 1 second, please wait. If a rank of A is less than n, if rank of A is less than n, the system has a non-trivial solution. Moreover, the solution set has n minus r independent solutions. If you have thorough with the non-homogeneous model, and obviously we have to eliminate actually one case that is called no solution case. And here, one solution is always clear. Such a solution is called a trivial solution. Now, I want to take one example on this, because remember that we are doing one problem, homogeneous problem, as we feel that it is one problem. Such a type of three problems completes one eigenvalue eigenvector problem. And this model is useful for us in diagonalization of a matrix. Actually at this level it is called one problem, but such a type of three problems will completes actually one problem, that is called diagonalization of a matrix, or whether the matrix quadratic form to canonical form, or eigenvalues and eigenvectors of a matrix. Solve the system of equation. There are three equations are available. So clear that 0, 0, and 0. It is called a homogeneous system. There is no need to bother. One can definitely say that x is equal to y is equal to z is equal to 0 is a solution. There is no need to solve any system. We can easily or directly say that it is a solution. But my concentration is, can we get any non-zero solution or not? So for that, when it is the homogeneous system, please don't take a capital K. Please don't take K. There is no need to go for K. Just to take only the coefficient matrix. Even if you take a K, the meaning of K is equal to capital A together with the capital B. Suppose if you are interested to take the last model, capital K is equal to, it is 0, 0, 0 that we have to add. By adding the matrix, use any operation. There is no change in the last column elements, always zeros. We have to write once again 0, 0, 0. We have to write once again 0, 0, 0. Instead of writing zeros that many number of times, just we are eliminating or we are deleting the last column. Let us go for please wait, I want to remove this last column elements. There is no need to take a K, just only A is sufficient in case of homogeneous system of equations. So our focus is it possible to find a non-zero solution or not? So as it is the first non-zero element, we want to make these two elements are equal to 0. As it is 3, use the operation R2 minus 3R1, as I mentioned here. And to make the number 2 is equal to 0, R3 minus 2R. By applying those two operations, these two elements are equal to 0. But luckily, we are getting these two elements are because this row is identical with this third row. As it is the first non-zero element of the second row, I want to use the operation R3 minus R2, or R3 gives R3 minus R2. We will get this element is also equal to 0, this is equal to 0. Here rank of A is equal to 2. The rank of A is equal to 2. And there are three unknowns are available. It is X, Y, and Z. Rank of A is equal to 2, less than 3, the number of unknowns. So the system has a non-trivial solution. It has a non-trivial solution. Suppose if you are doing a problem and this number is, sorry, the last number may be 9, assume that. Then rank of A is equal to 3. The system has only one solution, that is called the trivial solution. What about the solution set of the system? Because it is the problem, always I want to keep the problem as it is to make it somewhat convenient for us. So rank of A is equal to 2, less than the number of unknowns. So the system has a non-trivial solution. In particular, the solution set has, remember that there is a terminology. The solution set has 3 minus 2 is equal to 1 parameter or 1 independent solution. Now, these equations are nothing but x plus 2y minus z. It is x plus 2y minus z is equal to 0, minus 5y plus 2z is equal to 0. If I take from the last equation, one can say that 5y is equal to 2z. If I take the value z is equal to 5k, assume that because I am completely away from the what we call as rational numbers, I want to go for some like integers format. There is no rule that you can take a k as any number. So if I take z is equal to 5k, this is 5. Please wait, I want to cancel that for our convenience. This is 5 and 5 will cancel. Then obviously y is equal to simply 2k. So if I take z is equal to 5k, then obviously y is equal to 2k. Substitute both the numbers in the first equation, you get the value of x. The value of x is equal to k. It is called a solution set, and I can take infinitely many values. Immediately there is if I take a k is equal to 0, of course, if you take a k is equal to 0, always a solution, there is no doubt. When you observe that, this is called a subspace of the vector space. It is called when you go for RQ. As I mentioned to you, several times I mentioned the vector spaces, but remember that R cube is the set of all the elements of the form X, Y, Z, where X, Y, Z belongs to capital R. It is a vector space of dimension 3, with 3 vectors. And this S will act as a subspace of R cube. It has one parameter is available. The dimension of this vector space or subspace, dimension of S is 1. So for the vector space R cube, you can call it as S is a subspace of the vector space, and moreover, you can call it as the dimension of the vector space is equal to 1. It is some simple, whenever it is required, just I want to mention, because these spaces are not just independent or related to matrices. These are definitely useful concepts when you go for linear transformations or linear algebra exactly. Please wait, I want to go for characteristic. I will discuss the that is called circuit at the end, because I want to complete first of all the known numbers first of all, then I want to go for the applications. Now please wait, I want to go for something like a dark blue color. It is somewhat convenient. Characteristic equation and characteristic roots of a matrix. So if capital A is any square matrix of order n and I is an identity matrix of the same size, so assume that if a capital A is a 2 by 2 matrix, I is a 2 by 2 matrix. If A is a 3 by 3 matrix, I is a 3 by 3 matrix. If A is a 4 by 4 matrix and I is a 4 by 4 matrix. So we have to always take A and I are of the same size. Then determinant of A minus lambda I, it is called a polynomial of order n, is always a polynomial of order n, is equal to 0 is available. It is called an equation. It is after expansion, you get an equation of the form like this. It is called characteristic equation of the matrix. If A is any square matrix and I is an identity matrix of the same size, Then determinant of a minus lambda I is equal to 0. On expansion, we get an equation. This is called a characteristic equation of the matrix. Of course, it is called a polynomial in terms of n. Already you know that how to find the roots of a polynomial at your 7th class or 8th class standard. So we'll get a maximum 3 roots. So this is a polynomial and we can have at most n distinct roots. Sometimes they may be distinct, sometimes they may be equal, sometimes they may be pair of complex conjugates. That depends on the matrix. So each root of the characteristic equation is called a characteristic root or eigenvalue or latent root or latent value. Now, I will have some properties of the eigenvalues. So if lambda 1, lambda 2 and so on lambda n are the eigenvalues of a matrix capital A, then the sum of the eigenvalues is equal to sum of the principal diagonal elements. It is one property available for us. Sum of the eigenvalues is equal to sum of the principal diagonal elements, and the product of the eigenvalues is equal to determinant of the matrix. That is, you can call it as lambda 1. Please wait. Lambda 1, lambda 2, and so on. Lambda n is equal to product of the eigenvalues is equal to determinant of the matrix. And if lambda is an eigenvalue of capital A, then lambda power m is an eigenvalue for A power m. Just we'll discuss the things when we are doing a problem. The values, the eigenvalues of a triangular matrix, it may be an upper triangular matrix, lower triangular matrix, or a diagonal matrix. Remember that I mentioned three problems like this: 1, 2, 3, 0, 4, 5, 0, 0, minus 7. All of you know that it is an upper triangular matrix. Then obviously your principal diagonal elements, the numbers 1, 4, minus 3 are the principal diagonal elements. These are called the eigenvalues. Even the matrix, I want to call special matrices, especially. So the three matrices are nothing but upper triangular matrix, lower triangular matrix, or a triangular matrix. In all the three cases, your principal diagonal elements are your eigenvalues. Then I want to find the eigenvalues of the matrix. I'm not calculating an eigenvectors at this level. Now look at solution. Characteristic equation of the matrix capital A is A minus lambda I is equal to 0. In the first case, please wait, I want to take a different color. So I want to take a different color. There is no way. Capital A is equal to 5, 4, 1, 2. By that time, I want to take same size identity matrix. Capital I is equal to 1, 0, 0, 1. If you take determinant of A minus lambda I, it is if it is I, if you take lambda I, it is nothing but lambda 0, 0, lambda. If you look at A minus lambda, it is A minus lambda I. Determinant, it is 5 minus lambda. It is 4, 1, 2 minus lambda is equal to 0. Of course, I already mentioned here, I forgot it. So, on expansion of the determinant, it is a 5 minus lambda into 2 minus lambda minus 4 into 1, that is equal to 0. So, we have something like lambda square minus 7 lambda plus 6 is equal to 0. If you are interested, look at this polynomial is called a monic polynomial. There are some properties that are available from the modern algebra. This is called a monic polynomial. What is the meaning of a monic polynomial? Monic polynomial is a polynomial whose leading coefficient is 1. And moreover, the roots of the polynomial are roots of the constant term. Roots of the polynomial are roots of the, so the roots of 6 are nothing but 1 is a root, minus 1 is a root, 2 is a root, minus 2 is a root, please wait, 3 is a root, minus 3 is a root, then 6 is a root, minus 6 is a root. Only these numbers are roots of the polynomial. No other number will act as a root of the polynomial. It is somewhat simple point that is useful for you. Remember that as far as real numbers are considered, only these numbers are possible roots of the polynomial. So look at the sum of the coefficients. Lambda square coefficient is 1. Lambda coefficient is minus 7. And the constant term is 6. By adding all the three numbers, the resultant value is equal to 0. So 1 is the root of the polynomial.
Oh,
If 1 is the root, we can easily find the second root, that is equal to 6. At this level, we have a little bit doubt whether the two roots are correct or not. Look at 1 plus 6, that is equal to 7. Look at the sum of the principal diagonal elements. It is nothing but 5 plus 2, that is equal to 7. Which shows that at least at one step, we can verify that our answer is correct or not. Sum of the eigenvalues is equal to sum of the principal diagonal elements. So suppose if I want to find, once I know capital A, please wait, I have capital A is available. And my interest is what about the eigenvalues of A power 2025? So there is no need to calculate A power 2025 because it takes a lot of time, but I can tell what are the eigenvalues. As the eigenvalues of A are 1, 6, please wait. So the eigenvalues of A are 1, 6. The eigenvalues of A power 2025 are 1 power 2025 and 6 power 2025. I'm not interested to calculate, just for information sake that I want to tell to you. So as 1 power 2025 is equal to 1, it is so comfortable, but it is not that much easy to mention. So the eigenvalues of A cube, eigenvalues of A cube are nothing but simply 1 cube and 6 cube. There is no need to calculate any A cube. We can mention or we can find comfortably the eigenvalues of A square, A cube, A power 4, and so on. Suppose
sir,
if we have the
excuse me,
eigenvalue.
sir.
Sir, can you repeat, sir?
Just a minute, sir. I think Smita Gowda.
Okay.
I think they have any questions they will ask, sir. Smita Gowda, you
Can
can
you,
unmute and you can ask if you have any question. Unmute yourself and ask that question.
please ask your question.
Smita Gowda. Bhumika GR. You can ask if you have any doubts. You can ask Bhumika GR. Do you have any doubts?
And also please ask related to the current topic.
Rupa AE. Do you have any doubts as you raised your hand? Is there any
Please
doubts?
unmute your mic. Please unmute your mic and ask your question. Please unmute your mic when you're asking the question. Please unmute. Otherwise, it is not audible for us. Or post your question in the chat box. At least we can see that what is your interest of question.
You can unmute if you have doubts. Bhumika GR, Smita Gowda, and Rupa AE. If you have any doubts, you can unmute yourself and ask your question. Sir, kindly continue, sir.
Yes, sir. Thank you. So those who are having any doubts, please raise your hand or put your question in the chat box. It is somewhat comfortable to clarify your doubt. I'm repeating that those who are having any doubts, please post your question in the chat box or you ask me directly by unmuting your mic. Otherwise, it is not audible for us. Is it okay, sir?
Yeah, fine, sir.
Okay, sir. I will go continue the class. Right. Now, I want to take the next example because it is in the previous we can discuss about a 2 by 2 matrix. Now, I want to discuss about a 3 by 3 matrix. Now, we have a 3 by 3 matrix. Please wait. I will take a 3 by 3 matrix. As B is a 3 by 3 matrix, I want to take the same size identity matrix of size 3, which is 1, 0, 0, 0, 1, 0, and 0, 0, 1. So once it is I can take it as a lambda I with the principal diagonal elements are equal to lambda, lambda, and lambda. If you take b minus lambda I, we take b minus lambda I, 2 minus lambda, subtract lambda from the principal diagonal elements, 1 minus lambda, and minus 3 minus lambda. On expansion, we'll get it as 2 minus lambda into 1 minus lambda into minus 3 minus lambda minus 2 and so on. This is the characteristic equation of the matrix. In other words, which is same as lambda cube. I want to just mention, multiply every term with the minus 13 lambda plus 12 is equal to 0. But whereas this example is not, this polynomial is not monic because your leading coefficient is equal to minus 1, but whereas it is called a monic polynomial. And remember that as the 12 is the constant term and the divisors are nothing but simply, I want to take only positive numbers, 1, 2, 3, 4, 6, and it is 12. Definitely, only these are the divisors for the constant term. So only these are the possible roots of the polynomial, maybe plus or minus, remember that. So as the sum of the coefficient, lambda cube coefficient is 1, lambda square coefficient is 0, lambda coefficient is minus 13, and the constant term is 12. As the sum of the coefficients is equal to 0, when you add all the terms, 1 minus 13 minus 12 plus 12 is equal to 0, one can definitely say that lambda is equal to 1 is a root of the polynomial. We can apply synthetic division method to get the remaining roots. As you know that lambda is equal to 1 is a root of the polynomial, you can take something like this. Lambda is equal to 1. As lambda cube coefficient is 1, lambda square coefficient is 0, lambda coefficient is minus 13, and the constant term is 12. So if we take the first place is occupied with 0, 1 plus 0 is 1, 1 plus 1, sorry, 1 into 1 is equal to 1, 1 into 1 is equal to 1, minus 13 plus 1 is equal to minus 12, minus 12 into 1 is equal to minus 12, that is equal to 0. Even if you use your calculator to get the values directly, that is a different thing. So the polynomial becomes lambda minus 1 into, it is becomes lambda square plus lambda minus 12 is equal to 0. So it is lambda minus 1 and the factors are 4 and 3, lambda plus 4 into lambda minus 3 is equal to 0. So your eigenvalues are nothing but lambda is equal to, it is 1 minus 4 and 3. 1 minus 4 and 3, as we mentioned here. The more important is when you are in the examination hall, after completion of this work, you may have a little bit of whether they are correct or not. Look at the sum of the eigenvalues. Sum is equal to 0. Sum of your principal diagonal elements is also equal to 0. It is the first test to say that your eigenvalues may be correct. Does not mean that exactly correct. It is one test to say that your eigenvalues are correct. So the possible eigenvalues may be, suppose there are 3 roots are available. So assume that the roots may be, as I mentioned, it is 1, minus 4, and 3. You can call it as all the eigenvalues are distinct eigenvalues. Sometimes all are equal, sometimes 2 different and 1 equal. So there are 3 possible cases that are available for us. 3 distinct, maybe 2 equal, 1 distinct, and you make it as all the 3 or 3 eigenvalues are distinct. Now I want to discuss about the characteristic vector of a matrix. Correspond to every vector, correspond to every eigenvalue lambda, it capital A be the square matrix of a non-zero vector capital X, because it is a more important concept in vector spaces. A non-zero matrix capital K of size n by 1, it is called n rows and 1 column, is said to be the eigenvector of capital A correspond to the eigenvalue lambda. It is satisfies Ax is equal to lambda. It is a more important equation. Remember that I'm repeating it is more equation important. So if Ax is equal to lambda x is available for the matrix capital A, then lambda is said to be the eigenvalue and capital X is said to be the corresponding eigenvector. If lambda changes, auto
Rangaswamy. If you have any doubts, you can ask, unmute yourself and ask. As you have raised your hand, Rangaswamy. Kindly unmute. Rangaswamy, yes. Do you have any doubts?
At least say, okay.
At least the at least you can say, if you don't have any doubts, you can say no. Continue, sir. Thank you, sir.
Okay, sir.
Sorry, and
Okay,
continue.
please. No problems. At least we are here actually at least to clarify some of the doubts where they cannot ask some of the questions in the classes at least.
Okay.
Now, so let capital A be an eigenvalue of the matrix capital A. It is lambda is an eigenvalue for a matrix capital A. As I mentioned to you, remember always what is the meaning. Always the student may have doubt. What is the meaning of this lambda? So the meaning of that is, please wait. I want to remove this one actually. There are several values. Oh, please wait. I want to just tell one point before going for the eigenvector. Taking that's my time. Please wait. I want to tell one point to you related to the eigenvalues. I want to stop here. Remember that there is a eigenvalue lambda is equal to 1 is an eigenvalue. Suppose if you subtract 1 from the principal diagonal elements of B, it is 2. Subtract 1, it is 1. Keep all the elements as base. 2 minus 7, it is 2. As I mentioned, subtract 1 from the principal diagonal elements 0, 2, it is 0, 1, minus 3 minus 1, minus 4. If you find the determinant of this matrix is equal to 0. So whenever you are calculating the eigenvalues, after subtracting 1 from the principal diagonal, the determinant of the matrix simply becomes 0. Similarly, when you subtract 3 from the principal diagonal, the determinant of the matrix is equal to 0. If you subtract minus 4, I think all of you know that subtracting of minus 4 is nothing but adding 4. The determinant of the matrix is equal to. So rather, after subtracting these 3 numbers, the resultant of that is called the resultant matrix has a determinant 0. So those 3 numbers are called eigenvalues of the matrix. But when you go for the signals and systems, if the eigenvalue is negative, definitely the system has a stability. Otherwise, the system is said to be unstable. Now, let us go for continuation of the class. So, let a capital X be an n by 1 matrix. So, that vector is said to be, it is called a column matrix. All of you remember that it is called a column matrix of the form some x1, x2, and so on, xn. So, a column matrix is said to be the eigenvector of capital A correspond to the eigenvalue lambda. If Ax is equal to lambda x, in other words, it is A minus lambda I into x is equal to 0. Now, as I want to take the only previous example, because some of my work is reduced. Okay, please wait. I want to go for the previous example. Right. It is only B or not. Okay, right. Capital B is the matrix which is equal to 2, 2 minus 7, 2, 1, 2, and so on. We already calculated the eigenvalues are 1, 4, and minus 3. Once again, I want to tell to you sum of the eigenvalues is equal to sum of your principal diagonal elements. There is one more property, product of the eigenvalues. Suppose so, for the matrix, the determinant is required for you. Determinant of the matrix is equal to product of the eigenvalues. It is equal to minus 12. Now, I want to take the matrix. I want to first of all, I want to take x1 is a column matrix minus 1, 4, 1. I want to multiply the matrix capital B with a capital X1. I got the same thing, which is 1 into minus 1 into 4, 1. So it is exactly of the form. This is a capital B into capital X is equal to 1 into capital X. It is exactly of the form Ax is equal to lambda x format. If something will happen, 1 is said to be the eigenvalue of capital B and x is said to be the corresponding eigenvector. But here already I mentioned capital X1. The next our concentration is how to calculate capital X1. Now, we can observe that capital B into x1 multiply capital B with x1 minus 2 into 1 minus 2 plus 8 6 6 minus 7 that is equal to minus 1. Similarly, second and third elements, your answer is equal to 1 into x1. So x1 is said to be the eigenvector of capital B corresponding to the eigenvalue lambda is equal to 1. Now we want to find the eigenvectors correspond to the remaining elements. As we mentioned, the matrix has three eigenvalues, 1, 4, and minus 3. In one case, just I mentioned directly, then I want to find the eigenvector corresponding to lambda is equal to 4. So using the matrix B and 3 in the above equation, we have, I want to find the eigenvector corresponding to eigenvalue lambda is equal to 3. Now consider B minus 3i into x is equal to 0. Subtract 3 from the principal diagonal elements of capital B. As I mentioned to you, subtract 3 from the principal diagonal elements, it is nothing but like this. Now reduce the matrix into the, remember the right hand side is only simple 0, but actually it is not a 0, it is called a 0 vector which contains 3 zeros. Which contains 3 zeros. Here also which contains 3 zeros. It is, there is no need, there is no mistake actually, it is the representation, nothing wrong in that time. If I understand that, let us take it as 3 zeros. Now, reduce the system into the echelon form. So I want to make the number 2 is equal to 0 by using the operation R2 plus 2 R1. So it is nothing but like this. 2 is equal to 0. Multiply first row with 2. Add the elements to the second row. It is a 4 minus 2 is equal to 2. It is a minus 14 plus 2 that is equal to minus 12. And it is 0, 0. Then it is the, I want to make this element is equal to 0 using the operation R3 gives. It is a 2 R3 minus R2. Already, I think it was mentioned already. 2 R3 plus R2. Such a type of operations is not allowed in determinants. Remember that I'm repeating. Such a type of operations are because only in the equations it is allowed. You can multiply any row by a non-zero constant. Such operations are allowed only in the matrices or a system of equations, but not in the determinants. If in the determinants, if you want to multiply any row with 2, immediately you have to divide with 1 by 2. We divide with 2, not 1 by 2. So let us look at now here the number of let us go for, please wait. I want to take some other color. So it is the first non-zero row, second non-zero row. So rank of A is equal to 2. The system has definitely a non-trivial solution, and it is the eigenvector corresponding to the eigenvalue lambda is equal to 3. Similarly, we can find lambda is equal to 3. It may be not 3, it may be, please wait, I won't take it is the eigenvalue 1, 3, 1 minus 3 and 4. So we can find the eigenvectors and eigenvalues. Eigenvalue is nothing but determinant of A minus lambda I is equal to 0. And expanding the determinant, you will get a third degree or nothing but a fourth degree polynomial. So the roots of the characteristic equation are called eigenvalues or latent roots. Correspond to every eigenvalue, we can find a non-zero vector. Remember that always it should be a non-zero vector. Please wait, I want to mention already as I mentioned. So a non-zero vector capital X is said to be eigenvector of the matrix if Ax is equal to lambda x. Now let us go for independent set of vectors. So a set of vectors x1, x2, and so on xn, because these concepts are useful in diagonalization of a matrix. A set of vectors x1, x2, x3, and so on xn are said to be independent if there exist scalars a1, a2, and so on an. Remember that not all 0. Some may be 0, but not all 0. Such that a1 x1 plus a2 x2 and so on an xn is equal to 0. Such numbers a1, a2, and so on an are available, then the vectors are said to be linearly independent. Otherwise, they are said to be linearly dependent. Example, the vectors 1, 0, 0, 1 are independent. How can we say that? So let us take before that first vector, call it as 1, 0. As b into the second vector 0, 1 is equal to 0, 0. When you solve the equations, you will get only A is equal to 0 and B is equal to 0. So you cannot find any non-zero scalars so that the linear combination is equal to 0. So the two vectors are set linearly independent. But if I want to take these three vectors, there is a into minus 3 into first vector plus 1 into second vector plus 1 into third vector. If I add minus 3 into 1 minus 3 plus 1 minus 2 plus 2 is equal to 0. Similarly, minus 3 minus 1 minus 4 plus 4 0. So at least one coefficient, remember that at least one coefficient is not equal to 0. So the three vectors are said to be linearly dependent. Because of these concepts are useful in principle, I can call it as a diagonalization of a matrix. Note that the eigenvalues of a square matrix, or if the eigenvalues, remember, note that if the eigenvalues, the more important, of a square matrix are distinct, then the corresponding eigenvectors are linearly independent. But if they are equal, but we cannot give any guarantee that the eigenvectors are dependent or independent. So in the previous example, these are the eigenvalues of the matrix, and these are the corresponding eigenvectors. With the same note, we can conclude that these three vectors are linearly independent. Suppose if you have eigenvalues of 1, 2, 2, we cannot give you any guarantee that the eigenvectors are linearly independent. There is no guarantee, but we have to check based on the rank of the matrix. Find the eigenvalues and the corresponding eigenvectors of the matrix. So now I consider a matrix of the form 3 by 3. I calculated because in the previous example, all the eigenvalues are distinct, but here I want to consider two eigenvalues are equal and one eigenvalue is different. So since the eigenvalue, please wait, since the eigenvalue minus 2 is exactly contains one time, so the algebraic multiplicity of the eigenvalue is called 1. Because the number 2 is repeated 2 number of times, your algebraic multiplicity of the matrix is equal to 2. So if it is repeated 3 number of times, its algebraic multiplicity is equal to 3. That depends the number of times the eigenvalue repeated. If the eigenvalue is repeated exactly one time, then it is called algebraic multiplicity is equal to 1. If it is repeated 2 times, then it is called algebraic multiplicity is equal to 2. Now, for the matrix, as I mentioned, minus 2, 2, and 2 of the eigenvalues corresponding to lambda is equal to minus 2. After applying echelon form, the eigenvector is nothing but minus 4, minus 1, and 7. Correspond to lambda is equal to, because algebraic multiplicity, because the root is exactly obtained one time, so algebraic multiplicity is 1. We can find one eigenvector, so one can say that its a geometric multiplicity is also equal to 1. Suppose if I want to go for lambda is equal to 2. If I take lambda is equal to 2 and apply on the operations, I will get rank of the matrix is equal to 2. So I have only one independent eigenvector. I cannot find two independent eigenvectors.
Sir,
As I cannot find two.
Doctor, I think one of them have raised their hand.
Okay,
Dr.
sir.
Chitra. Dr. Chitra, do you have any doubts? You can unmute yourself and clear your doubts.
Sir, you are already given permission for all the students, sir, for unmuting?
No, sir, I have not given.
No. Okay, good. Okay, sir, is there any questions in the chat box, sir?
No, sir, I have not received.
Not received. Okay, good.
They are telling that no doubts.
Okay, okay.
You can continue, sir. They didn't ask.
Okay, sir. Okay. 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 So when I take lambda is equal to 2, and by taking b, it is a b, I think a minus 2i, and reducing the matrix into the echelon form, we have two non-zero rows. So rank of A is equal to 2.
ಅಲ್ಲ ಅಲ್ಲ ಇವಾಗ್ಲೇ ಅಲ್ಲ ಆಮೇಲೆ ಕರಿತೀವಿ ನಾವೇ.
So x2, I will get only one independent vector. It is not possible to calculate or to find second independent eigenvector. So we can call it as algebraic multiplicity is 2, as I mentioned here. We cannot find the second eigenvector. So geometric multiplicity is 1. The meaning of that is we can calculate only one independent eigenvector, but not to two independent eigenvectors. The doubt is when we will get to two independent eigenvectors. If your second row is a completely 0, then rank of A is equal to 1 and the number of unknowns is equal to 3. By that time, we'll get to two independent eigenvectors. Here, in such cases, you can call it as the defect of the eigenvector is equal to algebraic multiplicity minus the geometric multiplicity. Algebraic multiplicity is nothing but 2 because the value is repeated to 2 number of times. And we calculate to only one eigenvector, that is called 1. So it is called defect of the eigenvalue is equal to 1. Reduce it to diagonal form. This is the last model. So let us go for capital A is any square matrix. I want to go for 3 by 3 because if you go for 4 by 4, it takes a lot of time. Let capital A be any 3 by 3 matrix. Lambda 1, lambda 2, lambda 3 are the eigenvalues. And x1, x2, x3 are the corresponding eigenvectors. Then the matrix capital P is obtained. Each column is equal to one eigenvector, x1, x2, x3. Then AP is equal to PD, or in other words, P inverse AP is equal to capital D. D is called the diagonal matrix. In the diagonal matrix, the principal diagonal elements are eigenvalues of the matrix. So the square matrix capital A cap of order n is similar to a square matrix capital A of order n if A cap is equal to P inverse AP for some non-zero matrix capital P. If you apply simply D is equal to P inverse AP, you can call it as A is equal to multiply towards left side with P, right side with P inverse. A power n is equal to P into D power n into P inverse. It is one simple example of finding the power of the matrix capital A. So for the matrix capital P, transform the matrix to diagonal form, then find A cube also. So like in the previous, find the characteristic equation of the matrix, will get something like this. As I mentioned, the matrix is, the equation is not monic, but I can make the problem as lambda cube minus 7 lambda square, of course, plus 36 is equal to 0. A simple technique once again here also. The sum of your principal diagonal elements, it is 157, is equal to 7. One can easily check that. So the eigenvalues are minus 2, 3, and 6. As all the three eigenvalues are distinct, the corresponding eigenvectors are linearly independent. Take the matrix capital P in which first eigenvector as the first column, second eigenvector as the second column, and the third eigenvector as the third column. Definitely, because they are independent, the matrix capital P has a determinant not equal to 0. As P determinant not equal to 0, P inverse exists. That is the nature of your linear independent set. So the matrix capital P is available and the determinant of P is equal to 6, and we can find P inverse, the inverse of the matrix, P inverse AP is equal to capital D. And we can find the DQ, the value that is called the matrix. As D is nothing but a diagonal matrix, D cube is minus 2 cube, 3 cube, and 6 cube. And A cube is equal to like this. So I won't stop here, sir. Any questions related to the topic? Because actually we have to apply these system of equations for circuits. Once again, this system of the matrix method is useful to encrypt or encode or decode the system. It takes some more time to complete those two topics also. Vasant Kumar sir, any doubts?
Sir?
Any doubts from the students?
Somebody is asking where we can use it in real life.
Sir, this system, okay, if they want to just, I want to show one more slide for them. It is somewhat convenient for them. Let us please wait. Please wait.
Somebody is asking how you find eigenvalue.
Eigenvalue.
Yeah.
So once we have the matrix capital A is available, by taking the same size identity matrix and finding the characteristic equation determinant of A minus lambda I is equal to 0, we can find the characteristic equation, and then from the roots of the characteristic equation, we can call it as eigenvalues of the matrix.
Somebody is asking, can you share the PPT?
Definitely, sir. After completion of this class, I will share it. No problem. This is please wait. I will to share one more time related. Sir.
Dr. Anand Kumar, you can raise your hand. I will make you to enable your mic.
Yes, they're saying okay, sir. Metro. Some RTTs typing.
Wait, sir. From Anand Kumar. Yeah. Anand Kumar, you can unmute and you can ask your doubt. Sir, Dr. Anand Kumar, sir. I'm enabled, sir. You can unmute yourself, sir.
Hello.
Sir. Sir, please, sir.
Am I audible?
Audible,
Yes,
sir.
you are audible. You can ask,
Okay.
sir.
Sir, if a matrix A can be written in the form P D P inverse, where D is the diagonal matrix, then D contains eigenvalue of A as its principal diagonal.
Yes, sir.
Am I right?
Yes. When the matrix capital P contains the eigenvectors as nothing but
eigenvector of the
same
matrix A.
With the same order, sir. If lambda 1, lambda 2, lambda 3 are the principal eigenvalues, principal diagonal elements of the diagonal matrix,
Yes.
then the matrix capital P contains the first column as the first eigenvector, second column contains second eigenvector, and the third column as third eigenvector.
Yes.
Provided,
then in
remember
this
that,
case,
provided we can write it as only if the corresponding eigenvectors are linearly independent. Otherwise, we cannot diagonalize the matrix, sir.
If the in this case, the matrix D has eigenvector same as the matrix A.
Can you repeat it, sir?
Sir, in this case, if eigenvector of A are linearly independent, then and A can be written as PDP inverse.
Exactly.
In this case, the matrix A and the matrix D has the same set of eigenvectors.
A and capital D, capital
Yes.
P, capital A and capital P or capital D. Because on the right hand side, we have two matrices. P inverse AP is equal to capital D. Is it right, sir? Or
Yes.
capital D is equal to P inverse into D into capital P.
Yes.
So my question is, eigenvalues of capital A and the eigenvalues of capital D, principal diagonal elements are equal.
Yes.
Because in capital D, the eigenvalues are your principal diagonal elements. Even capital A has the same set of eigenvalues. So eigenvalues of capital A and eigenvalues of capital D are the same, not related to capital P.
Yes.
And we have one more property. Similar matrices has the same eigenvalues if A is equivalent to capital B. Okay.
Okay, sir. Thank you.
Welcome.
Sir, another question is there. Does zero vector become an eigenvector?
No, sir. No, no, sir. By definition itself, a non-zero vector capital X is said to be the eigenvector if Ax is equal to lambda x. It is the definition itself. Zero vector cannot be eigenvector. Zero vector cannot call it as zero vector is an eigenvector. As I mentioned in the homogeneous system, the system of equations definitely has always a solution, zero solution. But our focus is to get a non-zero solution. Since zero vector is exactly because I don't exactly one of the participants mentioned zero. If zero vector is added to any set of vectors, the resultant set of vectors are linearly dependent but not linearly independent. So we cannot take a zero vector as an eigenvector. Right, sir? As some of the participants mentioned, if a zero vector is a vector in the that is called the set of vectors, it is a linearly dependent set but an independent set. If it is dependent, the corresponding eigenvector matrix is nothing but what we call it as a singular matrix but not a non-singular matrix.
Yes. Yes, exactly, sir.
Any questions, sir?
No more, sir.
Okay, sir.
Thank you so much for
Please,
sir, for the insightful and engaging session.
Madam,
We truly
One
appreciate.
second, one second.
but one minute, madam. Somebody
second,
asked about the textbook related to the vector spaces. Just I want to mention topics in algebra by I.N. Hairston is one of the best textbook. I'm repeating that topics in algebra by I.N. Hairston, Herstin. It is a book available in the internet. You can easily download. One more book that is called Bombry Abstract Algebra is one of the textbook available. And if you are interested, linear algebra, sir, please wait. Linear algebra by Krishnamurti is one of the best textbook for linear algebra. I'm repeating that for your modern algebra or vector spaces. Topics in algebra by I.N. Hairston, second edition. It is available in the internet. You can easily download. It is the first textbook. Second book, Abstract Algebra by Bombry, Bambri. It is one of the students-friendly textbook. If you are interested for linear algebra by Krishnamurti textbook is definitely useful for you.
Sir, good evening, sir.
Okay, sir.
Hello. Sir, am I audible?
Yes. Audible, sir.
Yes, sir. Good evening, sir. This is Purushottam from Bangalore.
Sir.
So I have a small doubt. Can I raise, sir, please?
Sir, please, sir.
So in the matrix, instead of numbers, can we use any like a trigonometric ratios like a sin theta, cos theta, or exponential, or any logarithmic function, sir?
It takes, sir, but this is called rotation or what we call it as rotation of the matrix. That is called a principal axis form that we are applying, sir. For the application, there are some applications are available where we can take, even suppose there is no need to go for that is called real numbers as our roots of the characteristic equation. Sometimes we may get a complex numbers. By the time we have to apply theta to get the standardization.
Exactly, sir.
Yes.
And I want to give a small comment about this question, sir. Actually, you have been explained. Sir, am I audible?
Audible, sir. No problem.
Actually, you have given a wonderful session, sir, really. So even I am taking some computer science subjects also. So for the artificial intelligence and machine learning. So there I observed what is the importance of the eigenvalues and eigenvectors. Really, you have been given a wonderful session, sir. It is very appreciable. And a few of them are asking, let me say something about my experience.
Okay.
So these eigenvalues and eigenvectors, they are using the image processor for image processing in the electronics and communication also,
Right.
and the natural language processing, and in the finite automata and theory of computations also for deterministic finite automata, for non-deterministic finite automata, for machine learning, and in the deep learning also they are using what is the importance of eigenvalues and eigenvectors. I know that. And even the robotics also to transform the vectors. Okay, the vectors can be supported for the robots. How to understand, how to give the movement to the left or right or top or bottom, whatever it is. While preparing that one, it is very important. And also has seen some one subject is the for artificial intelligence machine learning. That is the autonomous vehicles, actually. Autonomous vehicles. Okay. So their
Yes, sir.
autonomous vehicle nowadays it is very important, sir. Like a robot, so they are getting nowadays. We are seeing still in India we have not seen that driverless cars and driverless buses or something like a robot. So in the
Okay.
foreign, some of them implemented. So for
Okay.
them, actually, where to stop, where to control the vehicle, and how to avoid the signals, and how to follow the signals. As per the GPS can be supported through the vectors, okay, and linear algebra, and for gaming applications also, especially in the AI. Nowadays, we are playing some many games we are playing, and game designs. For example, PUBG also, for example, if we can take. So there
Okay.
also these eigenvectors, eigenvalues, the vector spaces. So simply, I suggested to the students also, those who are listening this one. So I request the students to follow in depth of the eigenvalues and the eigenvectors, not only restricted syllabus. Though VTU what he implemented, only that is following. That is not sufficient actually. I suggested to the students to follow in depth of the eigenvalues and eigenvectors. Thank
Actually,
you.
you are the yeah. Actually, you are in the computer science field. You know more applications related to eigenvalues and
Yes,
eigenvectors.
yes,
As you
I have
mentioned,
seen directly. I have seen. Yes,
as I mentioned to you, as you mentioned, it is definitely useful in image processing, signals and systems, as you mentioned,
yes, sir.
robotics and so on. And
Exactly.
when the syllabus is framing, they applied initially it is not possible to apply mathematics to all the fields at a time. So at least
Exactly.
in the first year, if they have these concepts, in the second or third year, syllabus related to eigenvalues,
Yes,
eigenvectors should be framed in the second or third year,
ex-
and the students may get very good touch with the subject, and they can apply the knowledge in their regular curriculum or core
yes,
subjects.
sir. Yes, sir.
Is it
Many
right, sir?
of them are saying other technical course faculty. What is the use of mathematics? What is the use of mathematics for them? Really, they don't know. I can say directly, sir. Really, they don't know because they can't supposed to apply without anything of applications of mathematics. It is not possible
Not
for
possible,
any
yes, sir.
preparing any project or something.
Even
So
to
thank you for your wonderful, sir.
even to write a program related to the arrays without matrix knowledge, they cannot write. All
Exactly,
of you
sir.
know, they at least they have to know the suffixes. What is the column? What is a row? What is an array? How to implement? How to check? All the things, definitely arrangement of the numbers. So matrix representation is known for them.
Yes, sir.
Okay, okay,
That's
sir. Thank
very
you, sir.
important, sir. So you have given a wonderful session, sir. Really, I am very angry to appreciate you. Really, it is very appreciable, sir. Really, and I thank to the Dr. Vasant Kumar for organizing this kind of sessions. Really, I am very interested. And also, I thank to the Seshatipuram College Management for conducting this kind of sessions. Sir. Really, thank you, sir. Thank you.
Thank you, sir.
Hello, sir. Am I audible?
Able, sir.
Hello.
Sir, it is audible, sir.
Okay, sir. I am Dr. A.K. Misra again. Sir, one more doubt. Uh, you have defined the
Yes.
determinant of a matrix,
Of a 2 by 2 and a
and
3 by 3
you have
matrix.
okay. You have defined that the determinant is a function
Yes, sir.
from a matrix to real number
Yes, sir.
instead of all real number.
Yes, sir.
But if my matrix contain the entry from the complex number, if we have a matrix one by one matrix I, then
Hmm.
its determinant is I, but this is not a real number.
No, no, sir.
So I
We
think
can no, sir. It does not mean that, sir. Because every function cannot be every relation cannot be a function. We can define a function correspond to every element of the correspond to every square matrix. We can assign a number. The number can be calculated from the given matrix with some property. That is called the determinant. Here only it is real valued function. If you define something like that, not in every case, sir. If we define like this, it is called a real valued function. If we define a
uh,
function like this, it
so
is
I
called a
think
real value.
my suggestion is that the codomain may should be must be complex number set. It means that determinant is a function from set of square matrices to a complex number.
When the right hand side is a real number set, it is called a real valued function. Suppose
Yeah,
if we define what is called as a function from domain set to complex field, it is called a complex valued function.
so
But
in
in the
general
general
case,
case,
we have to
we can
define from set of square matrices to complex numbers. Na, I think.
in the left hand side, if we have a complex number, right hand side there may be a complex number. Because the left hand
Yeah.
side, if you have only real numbers are available, we cannot get a determinant as a complex number. Is it right, sir?
Mhm. Mhm.
So that's what I'm saying. It is nothing but generally we are taking that we restrict our attention to only real numbers on the left hand side. So I
Yes.
want to define it because I want to go for right hand side also real numbers. If the left hand,
Mhm.
if I want to call it as roots of the characteristic equation, your answer and once again your point is more important. Roots may be
Mhm.
complex numbers.
Roots may be
It's
complex numbers.
may be complex number, but if the coefficient matrix, sorry, if the matrix capital A in the domain set is a real number, your answer is definitely a real number, cannot be a complex
Real.
number.
Yes.
Right, sir?
Okay. Okay. So thank you, sir.
Thank you,
Thank
sir. Kumar, sir.
Sir, is it audible?
Audible, sir.
Srinivas sir, if you are, I request you to provide the feedback of our national level seminar, sir.
Good evening to everyone. I am Dr. Srinivas Rao, Associate Professor of Mathematics at Bapatla Engineering College. I am grateful for the opportunity to participate in the two-day national seminar on expedition to the matrix world. The seminar was very informative and offering deep insights into both the theoretical concepts and practical applications of matrix algebra in engineering and scientific domains. The sessions were well organized and covered important topics such as the matrix transformations, eigenvalues, and eigenvectors, system of linear equations, etc. This seminar will definitely strengthen the problem-solving skills of students. I really appreciate the efforts of the organizers, the resource persons for conducting such a meaningful national level seminar. Thank you, one and all. Thank you, Vasant Kumar garu.
Thank you so much, sir, for your valuable suggestions and feedback.
Thank you, sir.
Finally, I will come to the conclusion of day two. Respected dignitaries, honorable resource person, faculty members, HODs, participants, research scholars, and dear students. As we come to the conclusion of this two-day national seminar, it is my honor to propose the vote of thanks. I express my sincere and heartfelt gratitude to Sri N. Karnakar, our resource person for day two, for delivering an excellent and thought-provoking session. His valuable contribution has greatly enriched this seminar and enhanced our understanding of the subject. I extend my deep gratitude to our management of Sheshadipram Educational Trust, our principal and HODs, and all administrative authorities for their constant support and encouragement in conducting this seminar successfully. My sincere thanks to all organizing committee members, faculty colleagues, and technical support team for their dedication and teamwork throughout the program. I also thank all the participants for their active involvement, insightful interactions, and enthusiastic participation over these 2 days. Finally, I thank each and everyone who contributed directly or indirectly to the success of this national seminar. With this, I formally conclude IMATH 2025 and wish you all continued academic excellence. Thank you and have a wonderful evening. Thank you all.
Thank you,
We are
sir.
going to share the feedback form in the WhatsApp group. You can provide your feedback, valuable feedback. Thank you all.
Thank you, sir. Thank you, Vasant Kumar garu.
Thank you. Thank you.
Thank you, sir. Vasanth Kumar garu.
Thank you. Thank you.